All right, thanks. So thanks for the invitation to present in this session. So I'm going to talk about confronting Earth system model trends with observations. I want to acknowledge my co-authors that are listed here, in particular Tiffany Shaw, who co-led this work. And so the topic here is kind of comparing our historical trends in Earth system models with observations and kind of trying to take stock of what we're doing well, where are discrepancies emerging, and then in particular in the context of this meeting, what should we be excited about as we move towards CMIP 7? So the content here is from this review article that was published last year, and this emerged from a US CLIVAR workshop that we had in the spring of 2024 to kind of gather experts together and take stock of how Earth system model trends are Earth system models are representing historical trends. And so the motivation for doing this now is, well, climate change is here now, and we have kind of almost a 50-year satellite-based observation record at this point, with this growing signal and a longer record, that we can really start to do more than we could even a decade ago in comparing historical trends in our models with those in observations. And so when we're comparing trends between models and observations, there are various different situations we can encounter. This is one that I think is taking up a lot of people's minds, and that's trends in the west minus east gradient in tropical Pacific sea surface temperatures. And this is a case where we're worried that we have a discrepancy. It's pretty clear something is going wrong. So we have an observed strengthening of that gradient, which is really at the edge of the CMIP 6 model distribution and at the edge or outside of what you get in large ensembles. And so we know there's probably something wrong. It could be a misrepresentation of the force trend, misrepresentation of internal variability, or some combination of the two. In some situations, it could also be issues with the observational record, although I think that's probably not the case in this one. And then we have situations where the models look like they're doing pretty well. So this is an example from Dong et al., who looked at the weakening of the Eurasian summertime jet stream. And so in observations here, you have a weakening, and this is very aligned with the model distribution. And so we don't have any reason to believe that there's a problem here. The model suggests there should have been a force weakening. The observations show that. Of course, we don't know how much of the observed trend is force versus internal variability, but we don't have reasons to be really concerned. Then we have really unclear situations, and so this is a case of the Southern Hemisphere storm track. So this is trends in vertically integrated eddy kinetic energy, and you just see that there's this massive observational spread, and so it really depends which observational data set you're using as to whether you conclude there's a problem or not. And then we also define partial successes, which is where we think the models are kind of doing things okay, but maybe there's something not quite right about them. So maybe they're getting the pattern of change okay, but the amplitude wrong, or maybe we're worried they're getting something right, but for the wrong reasons. And so in this review article, we kind of covered a bunch of different things from the literature in how models are doing, representing historical trends. And we tried to categorize them in this way into those 4 different categories, and that's kind of what we ended up with. So there are successes, there's just discrepancies, particularly the North Atlantic kind of jumps out as a region where we have a lot of discrepancies. There are partial successes, and then there are kind of unclear situations. And so obviously in a 10-minute talk or so, I'm not going to go through all of these, but I'll touch on a few of them. So let's start with the top of atmosphere radiative balance. So this is from Alenschek and Rugenstein, and it's showing the trend over the series record of the top of atmosphere radiation. So with warming, there's a net increase in top of atmosphere radiation, and they showed that this really lies either at the edge or outside of the model distribution. And so the number of potential reasons for this, one could be discrepancies in the post-2014 forcings. Of course, our historical runs only go up to 2014, and after that we're using scenarios for the forcings. Maybe atmospheric physics errors affecting the long wave and the short wave response to local warming, and then this issue of not getting the right pattern of sea surface temperature change that we already have discussed could be playing a role. And so I think one that's very simple thing, but looking towards CMIP 7, I think just having these longer historical runs with updated forcings is going to be really useful, particularly for problems like this where we just have a short record to begin with. And if we can kind of keep updating our forcings and updating our historical simulations, that will give us more and more opportunity to be comparing our models with observations. And I know there's efforts through CMIP. I haven't heard results from that yet. Maybe someone here knows the conclusion of that. But it'll be exciting to be updating our models with historical forcings as close to present day as we can. I've already touched a bit on the tropical Pacific gradient. I want to talk about that a little more in connections to the Southern Ocean. So this is the observed trends from a paper by Rob Wills. And then here's the multi-model mean sea surface temperature trend. And so Rob showed in large ensembles that this cooling in the Southern Ocean that you see in the observational record is kind of at the very edge or outside of the model distribution. And I think there's quite a lot of evidence at this point that that is connected to this issue that we see in the tropical Pacific, of in particular not getting this relative cooling in the eastern tropical Pacific. What's happening in the tropical Pacific is very closely connected to global mean temperature. So back at the time of the hiatus, Fife and Gillett did this analysis over a relatively short record and just showed how the global mean temperature here is correlated with what's going on in the eastern Pacific across the models. And so in this review article, we kind of reproduced that, but for the longer trends. And so this is all of the members from CMIP 6, and you can see global mean temperature scaling with the East Pacific temperature. And if we put the observations on here, you can see that the models that produce kind of a similar global mean temperature to observed are doing so with much more warming in the eastern tropical Pacific. But I think there's some hope that maybe we can improve on this with high resolution. So these are results from the 10-member MESACLIP project. This was using CSM1, run with a 1/4 degree atmosphere and a 10th degree ocean. And there's also one member on here, which is a higher resolution simulation from ICON. And you kind of get the sense that this distribution of higher resolution simulations has maybe shifted a bit to the left. More likely to get this cooling in the tropical Pacific, and in fact there's one MESACLIP member that's just perfect compared to observations. But it's pretty early to say. This is a limited number of models and members, but as we move to more models getting to this higher resolution, and these are not kilometer scale necessarily, but 10th degree simulations in the ocean. And if we can see that this is really a robust feature, that as you go to the higher resolutions, you're more likely to capture the pattern of SST trends right, then of course we would question what we're doing with the lower resolution models, or at least we'd want to understand how can we get the lower resolution models to do this right. I want to touch a bit on some circulation things in the summertime of the northern hemisphere. And so this is from a paper by Ray Chenke, and it's showing the trend in the summertime storm track in the northern hemisphere. And so he shows that in the observational record there's a weakening, and the models in CMIP 6 do pretty well at capturing that. But interestingly, the models in CMIP 5 in the blue PDF here, they didn't do as well at capturing this weakening of the summertime storm track. And so he's argued that there's an impact of the change in the forcings as you go from CMIP 5 to CMIP 6. And somehow something was more right about, or something about the CMIP 6 forcings was allowing the models to capture those trends. And he showed that, I think, by using some simulations from, I believe, CSM, where the CMIP 6 version of the model was run with CMIP 5 forcings. And so it's not just the models that are changing from one CMIP to the next, it's the forcings too. And so there's interesting things to discover as we move towards the new forcing data sets. While the models look like they're doing pretty well in the storm tracks in the kind of hemispheric average, that's not necessarily true locally. And so this is from a paper by Ian Baxter that's submitted. And locally, you can see that in these regions of the North Atlantic, there are regions where the storm track trends and the observational record are really lying outside of what the model distribution is capable of capturing. And this is pretty likely connected to recent studies that have also argued for this big increase in Greenland blocking events that is outside of the range of changes that the models are capturing too. Just want to finish up with more on the North Atlantic in the wintertime. It's pretty clear that we have some problems here in the North Atlantic. And so this is a figure that was actually shown yesterday from a paper by Russell Blackport. And what you see here is the trend and the strength of the 700 hectopascal zonal wind. And there are pretty large regions of the North Atlantic where these trends in era 5 here are lying outside of the distribution of what you can get in the models. And we've been looking at this too in these new simulations that have become available through the Large Ensemble Single Forcing MIP. So these are not single forcing runs, but we're just using the Large Ensemble historical simulations that are part of that project. And you see a very similar thing, and we have a pretty large number, 9 or so large ensembles, and these trends in the North Atlantic jet stream are really lying outside of the distribution of what you can get in these large ensembles. And these trends in the jet stream are connected to trends in the NAO. And so here's a time series of the NAO in these large ensemble simulations. The black is the observed trend, the blue is the ensemble mean trend, and then the blue dashed is the ensemble mean trend but scaled just so you can see it better. And so that there's kind of this argument going around that the ensemble mean in the model seems to be very highly correlated with the observations. I'm not quantifying that here, but there's only about a 5% chance of getting that high of a correlation between individual members and the ensemble mean as what you get in the observations. And so there's a lot of evidence for signal to noise issues in the North Atlantic from initialized predictions. And people are starting to make that argument for force changes as well, based on the fact that the ensemble mean signal is very highly correlated with the observations. I think personally, I'm not convinced of that yet. I think it doesn't have to be that the force signal is wrong. I think there could also be issues with just not representing low frequency variability and limited sample sizes in these short records where you have that low frequency variability. But I think it's a question we need to get to the bottom of, because if we're getting the force signal wrong, obviously that has big implications. So to conclude, we're gathering successes and discrepancies and partial successes and unclear situations in how well models are representing historical trends. We need more work to understand the discrepancies that arise, and I think there's a lot of exciting things that we can do with updated models and forcings and longer simulations through CMIP 7 to be getting as long of a record as we can to be comparing with our models. There's indications that going to higher resolution, not necessarily kilometer scale, but the resolutions that are now within reach for performing relatively large ensembles could help with the pattern of SST trends. And there is maybe some evidence of signal to noise issues in models that we need to understand and make sure it's robust and understand its origins. So thanks for your time.
Okay, thanks, Isla, for a great talk. We have some time for questions. If anyone wants to come to the microphones. Yeah, Andy.
Thanks, Isla. Can you comment on how many of these areas where trends are not reflected in the models, what the mean state bias in the models is like? I mean, I guess I'm picking out the Southern Ocean SSTs, which my eye was drawn to. We know the mean state is pretty wrong there, so it's not a big surprise that the trend is wrong. Are they all like that, or yeah, get a snapshot of that?
Yeah, it's a good question. I don't think there's always a clear link between the mean state biases and the trend. I mean, for the Southern Ocean, I know that CSM2 actually, like most models, have a jet that's too far equatorward. I guess that's maybe the bias that you're referring to. But CSM2 actually didn't. But it has a very good jet latitude. It has issues with the strength, but it still doesn't represent that cooling trend. I mean, I think that, yeah, we need to dig into that more, and having large ensembles where we can really quantify the mean state and the trend and look for relationships between them is going to be helpful. But I think it's not guaranteed that there are links between mean state biases and the trend biases.
Thank you, Isla. We have just produced a new large ensemble in the UK, and one analysis we have done, we have looked at these wintertime North Atlantic jet trend biases, and it depends a lot on the period you use. So we completely reproduce the results others have seen if you take the whole era 5 period starting in 1950. But then if you go to the satellite period, it looks all fine and consistent. So I'm not quite sure what to make of this result, but I was wondering if you could comment.
I agree. I think that's why I'm kind of skeptical about there being a signal-to-noise issue, is that we have so much low-frequency variability in the North Atlantic that I believe has a big natural component that we're not capturing correctly in our models. And so, yeah, it really could depend on the time period that you're looking at. And I think we've seen that already in the past. Like, there was a very clear positive trend in the NAO up to the year 2000, and everyone was making a big deal about that, and then, of course, it reversed. So I agree. In the paper, actually, I should have mentioned, Haim is going to talk about this on Thursday, and he'll show plots of the dependency of the start and the end date. And yeah, there's definitely a dependency. And I could imagine that there will continue to be a dependency as we move forward, that it doesn't look to me like something that's just going to keep on increasing, but I guess time will tell.
Okay, thanks.
Okay, we have one online, and then we'll go back to one on the floor.
So a question from Gavin asking about what about missing forcings, freshwater fluxes from ice sheets, anthropogenic dust, etc.
Yes, I should have mentioned that as a potential reason for discrepancies, as well as what I already mentioned. Yeah, I definitely agree. I think there's some evidence for the freshwater forcing in those Southern Ocean trend issues. And I think we can, like in the Ray Chemke's paper example, we could see that there was a change in the discrepancy through the forcings in going from CMIP 5 to CMIP 6.
Okay, one more, and then we better keep moving.
It's more of a comment. So these, in high-resolution models in the ERI project, we see some of the models show very strong convection in the Southern Ocean. That's not related to better capturing necessarily the SST pattern, but is due to the lack of the parameterization of the eddies, so that the model is convecting, so that's why the surface is cooling. I don't know how widespread this problem could be.
Yeah, I think there will be other people here that are better placed to answer that question. I think, I think definitely resolving the eddies in the Southern Ocean is a big part of why we see such a difference in those mesa clip simulations. I'm not sure about this particular issue that you've mentioned. I don't know if someone else here wants to chime in about that.
Okay, sorry, I have one very enthusiastic question to ask you here.
Mine's just a comment, just to say it's great that you highlighted the value of continually extending the forcing records, and we've got an opportunity to talk about that more on Friday morning.
Great.
Okay, thanks everyone. I'm sorry, we better move on, but please ask Isla questions in the break.